So our exam is going to be the Tuesday when you come back. That's officially the last day of school. Also, the quiz is due. Can you guys hear me in the back? Can you hear me in the back? Awesome. So that's the plan, and then I think we come back on Thursday to take your final exam. So everyone should take the final exam, even if you're having A. It replaces one low test score. If it's not lower, if it's lower, then I just drop the final. But everyone should take the final exam because of the evaluation, and we just want to see how good we're doing as teachers. All right, so let's start with the review for the test. All right, so the first thing we want to do is resonance. All right, so the first resonance structure, we have two of them. One of them is carbonate, and the other one is nitrate. All right, so let's do both of them. So what does resonance mean? Resonance basically means, multiple structures, okay? So we'll do carbonate first. So what is carbon happy at? 4. And what is oxygen happy at? 6 times 3 is 18. And what is the electrons? Okay, this means it gains 2 electrons. So we have 24 valence electrons here. All right, so remember with oxygen, how does oxygen work? Single bond oxygen, 3 lone pairs, or double bond oxygen, 2 lone pairs. Okay. All right, so with that being said, this is -2, so it will be C double bond O, and this is where our -2 comes in. Now, is that the only resonance structure? Is that the only resonance structure we can see? Where else could the double bond be? It could be on this side, so here. Okay, so you're going to put it backward, forwards. Okay, and where else could the next double bond be? On this side, right? So how will we do that? We'll move this pair of electrons here and that one there. All right, so make sure you are good at this. All right, can we do nitrate together? Okay, nitrate. This is N is happy at what number? 5. Oxygen's happy at 6. That's 18. The E minus is +1, so that's also 24 valence electrons. Okay, just like carbonate. Can you guys see this, or is this blurry? I bet you it's blurry. Alright, so how will we do nitrate? This is minus. Total charge is minus, so we'll do a single bond with oxygen. And then what about the other three? Okay, 2 double bonds. Very good. Okay, and there's that minus charge. There's that minus charge. And then what other resonance structures do you think can exist? We have that single bond over there. Where else can the single bond be? Okay, the single bond can be up top. And then where else could the single bond be? On this side, right? Okay, so notice here how the minus charges are delocalized. Here the double bond is delocalized. Okay. So there's a question on resonance there. Right? So make sure you are good with the resonance of a couple of these molecules. Okay, another one is cis-trans isomers. Okay, do you remember cis and trans isomers? Let's do that here. What is a cis isomer? Okay, first of all, what do you need? You need a double bond. And what does cis mean? Okay, cis means same side. Okay, same side of the double bond. And then where is trans? Opposite side. Opposite side. Okay, so we have cis and trans. Okay. Opposite double bond. Opposite side of the double bond. So whatever atom the substituent may be, okay, if it's on the same side, okay, it's the cis isomer. If it's on the opposite side, it's the trans isomer. All right, and okay, so make sure you are comfortable with the cis-trans situation. Alright, so we'll do some Lewis structures together. Okay, do we know the Lewis structure of ammonia? So here you want to bring table 10.1 and 10.2 to the test. Alright, so ammonia, water, formaldehyde. So these are some of the Lewis structures I'd like for you guys to know for the test. Shall we do a couple of these? Okay, not all of them, just a couple. Okay. So which one do you guys want to choose? Okay, I think we've done some of these in class. So how about SF6? Okay. What is sulfur happy at? 6. What is fluorine happy at? 7 times 6 is 42. So we have to get 48 valence electrons. So we have sulfur plus 6 fluorines. All right, so 1, 2, 3, 4, 5, 6. So is this the structure? Let's see if we have 48 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, and 48. I'm getting 48 all across. So how many bonds and how many lone pairs? 6 bonds and 0 lone pairs. So what does that make the structure? The electron pair geometry and the molecular geometry? Okay, they're one and the same. So what is their geometry? Look at table 10.1, and that would be octahedral. Okay. And what is the hybridization of this? Okay, sp3d2 hybridized sulfur. And is this polar or nonpolar? Okay, this is actually nonpolar, so it's nonpolar. All of these fluorines will cancel out with each other. The reason why I'm telling you guys it's nonpolar is because of symmetry. Okay, there's no lone pairs and they all cancel each other out. Yeah, they all cancel each other out, so this is nonpolar. Anything else you want to try? How about PF3 here? What is phosphorus happy at? 5. Fluorine is happy at 7. 7 times 3 is 21. We have 26 valence electrons. Oh, sorry. All right, so phosphorus. Okay, so happy at 5. 1, 2, 3. Okay, what did we say about halogens? Okay. How will halogens work? Okay, halogens will work with single bond and 3 lone pairs. Okay, so we'll do 3 lone pairs around this. Okay, 1, 2, 3, 4, 5, 6, 7. Okay, remember how to calculate formal charge in octet? Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, how about formal charge? 1, 2, 3, 4, 5, 6, 7. What is fluorine happy at? 7. So 7 minus 7 is 0. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Where will 25 and 26 go? Right? On the central atom. Okay, so let's do formal charge and octet for the phosphorus. Okay? 1, 2, 3, 4, 5, 6, 7, 8. So octet is fine. Let's do this. Formal charge. 1, 2, 3, 4, 5. What is phosphorus happy at? 5. What's 5 minus 5? 0. All right, how many bonds and how many lone pairs? 3 bonds, 1 lone pair. So what's 3 bonds and 1 lone pair? So here you want to look at table 10.2, which is the table that has the lone pairs. So what's 3 bonds and 1 lone pair? Trigonal pyramidal? So, but what is the electron pair geometry? Electron geometry is what? Tetrahedral. Okay, because you had 4, but we removed 4 and replaced it with what? A lone pair. Okay, so the electron pair geometry is tetrahedral, but it is not. It is not tetrahedral. Why isn't it tetrahedral? Because of the lone pair. So the lone pair imparts to it a molecular geometry that is, what will it be? What? Trigonal pyramidal, right? Trigonal pyramidal. And what hybridization is this? This is an sp3 hybridized phosphorus. Okay. And is this polar or non-polar? Okay, it's polar. Okay, it's asymmetric, so it's not symmetric. You know, the previous example, SF6 was symmetric, right? So it was non-polar. This is not symmetric because of the lone pair here. All right, anything else you want to do? Anything from this list you think you want some extra review on? Okay, how about cyanide ion? So cyanide ion, this is the structure, or this is the formula they give you. You want to find the structure. So what is carbon happy at? 4. What is nitrogen happy at? Okay, so plus 1. So we have 10 valence electrons here in the cyanide ion. And what do you think the central atom will be? Well, it's 2 atoms. You don't know which one is central, but we'll make carbon the central atom. Carbon loves what? Carbon is, how will we get 4 here? 2, 3. Okay. And then this is actually a more difficult problem. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So let's do the octet rule and the formal charge. Okay. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, what's the formal charge on the carbon here? 1, 2, 3, 4, 5. Okay. And what is carbon happy at? What's carbon happy at? 4. What's 4 minus 5?
1.
Minus 1. And then here, nitrogen 1, 2, 3, 4, 5, 6, 7, 8. That's fine. 1, 2, 3, 4, 5. What is nitrogen happy at? 5. What's 5 minus 5? 0. Okay. So that would be cyanide ion. Okay, is this polar or non-polar? Okay, this would be polar because nitrogen has more pull. Okay, nitrogen is different than carbon in terms of electronegativity. Okay, we'll skip the hybridization for this. Just so this would be 2 bonds and 1 lone pair. Is there 2 bonds and 1 lone pair thing? Molly? Do you know what's 2 bonds and 1 lone pair? Can I have that sheet here? 2 bonds and 1 lone pair. Okay, bent. Okay, there we go. 2 bonds and 1 lone pair is bent. So that's the geometry there. And what type of carbon is this? It's going to be an sp2 hybridized carbon. Alright, and anything else we can think of? Molecular geometry is bent. The electron geometry is trigonal planar. 2 bonds, 1 lone. Yeah, 2. Wait, 1 bond, 1 lone pair. 2 bonds, 1 lone pair. Yeah, anyways, we'll just go with that tree. Actually, you know what? I think I made a mistake here. I'm so sorry. This is 1 bond, 1 lone pair. Okay, 1 bond, 1 lone pair, which is linear. Okay. And this is an sp hybridized carbon. Huh?
No, I think that makes sense because it's literally drawing that way, so it has to be.
Yeah. Yeah. Anyways, yeah. Okay, cyanide is going to be linear and sp. Okay, it's a straight line. Okay, what if we do HCN? Okay, this is actually linear without the lone pair. Okay. That'd be hydrocyanic acid. Well, anyways, we'll not worry about this, okay? For those of you here in class or watching for the test review, okay, we'll just worry about hydrocyanic acid. Okay. All right. And this is an sp hybridized carbon. And is this polar or non-polar?
Polar.
Okay, it's polar. Okay. The nitrogen has a stronger pull than the carbon. Okay. All right, so any other Lewis structures? You guys know ammonia? Water. Okay, water is going to be bent, 2 bonds, 2 lone pairs. CH2O formaldehyde, we studied that in class a lot. Okay. SF6, hydrocyanic acid, PF3. So these are the Lewis structures: polarity, hybridization, electron pair geometry, and molecular geometry. All right, so make sure you are comfortable with all of these. All right. So this test is covering chapters 9 and 10, but also a little bit of chapter 8, so it's actually 8, 9, and 10. So do you remember our periodic trends? Okay, so the ionization is going to be higher as you go this way. This is called the first ionization energy. Okay, the energy required to strip an electron. So really, the highest electron energy, the energy that you need to remove an electron, is definitely highest over here. And the noble gases have really high really high ionization energy. It takes a lot of energy to remove these because they have a filled shell, if you remember that. Okay, so the largest ionization energy, you're looking in this area of the periodic table, and the first ionization energy actually lowers or decreases as you go down the group, because these are getting outer, and more outer. Okay. So which one is the highest ionization energy? You're going to look for something that's around here, the periodic table. And then the opposite is true for the size. The size. So for the size, actually, decreases across a group and increases down a group. Okay. So if you're looking for the largest size, you're looking around here. If you're looking for the smallest size, you're looking around here. Okay. So just picking the atom that has this largest size, look here. It's the largest size, look here. Okay, the smallest size, look here. More towards the right, it gets smaller and smaller in size. Okay, ionic radius. Okay, obviously something that's going to lose 5 electrons would be smaller than something that loses 2 electrons, like calcium ion, because this loses 5 electrons, right? And something that gains 2 electrons, it would be smaller, or something that gains 2 electrons would be smaller than something that loses or gains 1 electron. So, something like O minus 2 or something like that. Okay, so just remember, cations lose electrons, anions gain electrons. So these losing 5 electrons make it smaller. Okay, this should make some intuitive sense. Something that gains 2 electrons would be larger than something that gains only 1 electron. All right, and then we have a question here on sigma and pi bonds. Right. So if you have a double bond here, okay, we're just focusing in on the sp2. Carbons. Okay, so this double bond is actually 1 sigma and 1 pi. I actually have a bond for you. It's 1 sigma and 1 pi. So this is kind of like the overlap that you see here, okay? So here we have a sigma bond, which is a single bond, overlap of the s orbital, and a pi bond. Okay, so this is what a double bond would look like. All right, so we'll take across this. Here's there's one p orbital from here. Okay, the other p orbital recruited by this carbon atom. Is what a double bond would look like. And of course, you have the s orbital from this carbon and then the s orbital from this carbon. So that is what this would look like. Okay, so which is the sigma bond? Okay, it's the pink. And which is the pi bond? Okay, the p orbital overlap. It's here. So I think that's the exam. Okay, so there's a couple of multiple choice. There is some Lewis structures, and then resonance structures, nitrate and carbonate. Periodic trends. Okay, make sure you, from the multiple choice, you're able to pick out what is the largest, what is the smallest, which has the largest ionization energy, which has the lowest ionization energy. Okay, make sure you are good with the resonance, as I spoke about before. Okay, make sure you're good with these types of Lewis structures. We're looking at molecular geometry, electron pair geometry, hybridization, and whether it's polar and non-polar. All right, are there any questions on your end here? Okay, yeah.
On the, I think it was one we're at. I think it was like question 3. Study everything. Yes, that one right there. Do we have to write all of those 3, or you just
Yes, because it's resonance, all 3. It's not like one structure. This is actually all 3 fused into one. Yeah, and I would prefer if you write the brackets and the back and forth arrows. So, because you can't just get away with this one structure in the resonance. Okay, because this is just as equal and valid as this, which is just as equal and valid as this. Okay, so yeah, you want to do that whether it's carbonate or whether it's nitrate. All 3. Okay, this is the example of delocalization. Where is it?
Structure, right?
I'm sorry?
We're going to name the structure, right?
No, like draw the resonance structure of carbonate or draw the resonance structures of nitrate.
Okay. Sounds good.
Yeah. All right, anything else? All right, so turn in on Tuesday your quiz. Yes, thank you. Quiz, yeah. And then today turn in your lab report and your home and your notebook, and I'll put those points in on Canvas. All right. So have a good